Now that we know that we have a horizontal tangent at the coordinate 0, comma, 0.165, the question is still remaining, is this going to be a maximum or is this going to be a minimum? When we found out if we had maximum or minimums before in the past, we took our first derivative, or dy dx, and we placed those critical values on the number line. 4x minus 2xy over x squared plus y squared plus 6. Remember though, when we set dy dx equal to 0 and looked for those critical values, your number line was only in terms of one variable. We had to make sure that the derivative changed signs from positive to negative, or negative to positive, to see if we had a maximum or a minimum. This is a lot more complicated now though, because we have x's and y's together in this derivative. So how are we going to determine if it's a relative max or a relative min if we can't determine if the sign for the first derivative changes from a positive to a negative? Well, instead of using the first derivative, we're going to use what we call our second derivative test. The second derivative test says that you can actually use the second derivative to determine if you have a maximum or a minimum. So we're going to use the second derivative, or d squared y dx squared, to determine if we have a max or a min. If you look at the pictures above, notice that this coordinate here would be a maximum. If we have a maximum, notice that your graph is concave down. If your graph is concave down, that means that your second derivative, or d squared y dx squared, that is going to be less than 0. If we have a minimum, like this coordinate here, notice that the graph at that point is concave up. That means that your second derivative is going to have to be positive. So the more complicated part here is, all right, now that we have this expression, we're going to actually need to calculate the second derivative. So let's focus on finding our second derivative. To find the second derivative here, we're going to have to use a quotient rule. Now, this quotient rule, as we go through it, bear with me, it's going to be a little bit more complicated. However, the ones that you will calculate later won't be as difficult. Let's start. To use our quotient rule, we have our low, or our denominator, times the derivative of the numerator. Now, the derivative of the numerator, we'll start with taking the derivative of your first term here. That will just be 4. Now, we have to take the derivative of the next term here. Don't forget that this is actually a product. So we're going to have to use our product rule. We have the first times the derivative of the second plus the second times the derivative of the first. So this is low d high minus, I know guys, bear with, the top, or high, that's 4x minus 2xy, times the derivative of your bottom. The derivative of the bottom here is going to be 2x plus 2 dy dx, and then plus 0, because the derivative of 6 would be 0, since it's a constant. Recall that this is all over low squared. So that's x squared plus y squared plus 6 squared. It might be slightly more complicated here to determine the values, but recall we're using the coordinate of 0, comma, 0.165. We're going to take this value for x, and we're going to take this value for y and substitute it in. You might be able to help yourself by saying, all right, well, let's actually first figure out the value for dy dx. If we try to figure out the value for dy dx, we're going to plug it right into our calculator to find the values. If we start with 4 times 0 minus 2 times 0 times 0.165 all over 0 squared plus 0.165 squared plus 6. In our numerator, if you evaluate each term, that will just give you a value of 0. In your denominator, however, using 0.165 squared and adding 6 to that, our denominator becomes 6.027. That's a little bit of a rounded value. The derivative here, or dy dx, is actually going to be equal to 0. But if we have that information, we can actually use that to substitute in to our second derivative. Notice that the denominator here, x squared plus y squared plus 6, was the same as the denominator above. So when I substitute in that x and that y, it's just going to give me that number there. So we have 6.027. That's going to be multiplied by 4 minus 2 times 0 times your first derivative, which is 6.027, plus negative 2 times the y value, 0.165. We're going to subtract that from this term here. Note, now we have 4x minus 2xy, which we know is our numerator, this expression here above, which happens to be 0. And that will be times this term here. Now remember, since it's 0 times a number, that number doesn't actually really matter so much. And this is all going to be over 6.027 squared. Remember the value from your denominator, so that red value that we had from above. If we put this into our calculator, we have 6.027. That's going to be multiplied by 4 minus 0 minus 2 times 0.165, so just evaluating that numerator, and you'll actually wind up with 22.11909 divided by 6.027 squared, which is 36.3247. This number actually is a positive number. You can get a value for it if you'd like, but remember, all we're really interested in is whether that is positive or negative. So this number, which is actually equal to 0.6089, is greater than 0. That's a positive number. That means that your graph is concave up. If your graph is concave up, that means the point that we're dealing with, 0, 0.165, that point, that is going to be a minimum. If we hold off on a second and if we went to our Desmos app, we can actually justify this, gentleman, that this is exactly what's happening. If you take a look here, if I only show you the graph of the original function, the 2y to the third plus 6x squared y minus 12x squared plus 6y equals 1, if you look at that graph here, notice that we actually have a minimum at the coordinate right there. That coordinate is going to be right at 0.1652. In fact, the point that you have there, which has a horizontal tangent, is also a minimum. So it actually makes sense that what we justified here on notability of having a minimum at that point, because our graph is concave up, is absolutely justified.